Today we are going to discuss about the elementary particles, and especially we are going to focus on interaction and particle. As we all know, ordinary matter is composed of protons, neutrons and electrons. These particles seem to account for the structure of universe around us. All nuclides are stable. However, the neutrinos are needed for beta decay to take place. Indeed, without neutrinos, the reaction sequences that power the stars and can lead to the creation of elements heavier than hydrogen could not occur. The electromagnetic interaction between charged particles requires a photon as its carrier, and specifically, nuclear interaction between nucleons requires pions for the same purpose. Even so, only a few particles seem to be needed, and all of them has a definite role to play. Hundreds of elementary particles have been discovered till date, and all of which decay rapidly after being created in high energy collisions between other particles. That is, other particles are often created by the decay and the collision of high energy and higher energy collisions. And it has become clear that some of these particles called leptons and are more elementary than others, and that the others called hadrons are composites of far smaller number of rather unusual particles called quarks that have not been detected in isolation and probably never. So now let's move to the topic interaction and particles. The four interaction that we come across these days are strong forces, electromagnetic forces, weak force and gravitational force. These are apparently enough to account for all the physical processes and structures in the universe on all scales of size, from atoms, nuclei to galaxies and stars. The basic fundamental interactions are given in the table down. The As we can see, the strong forces are affected in particles like hadrons and quarks, and for electromagnetic force it is affected for the charged particles like proton and electron, and weak forces is affected by quarks and leptons, and gravitational force is observed and found in almost all the particles. So the list of fundamental interaction has changed over the years, and long ago the strong and weak interaction were unknown, and it was not even clear that the gravity pulls things down to earth. This we might call it as terrestrial gravity, and this gravity is same as to what the planets are holded in the orbits and are made to revolve around the sun. So one of the Newton's great accomplishment was to show that both terrestrial and astronomical gravity are the same. Another notable unification was made by Maxwell when he demonstrated that electric and magnetic forces can be both traced to a single interaction between charged particles. As we can see, the electromagnetic and weak interaction turn out to be different manifestations of single electro-weak interaction. This in turn seems to have links to the strong interaction, though the details of relationship are still not entirely clear. The final step in understanding how nature operates would be a single picture that includes gravitation, and the strong hints is that theory of everything is beyond reach. This is the flowchart or diagram of the goals of physics as a singular theoretical picture that unites all the ways in which particles of matter that interact with each other, and we can see in the diagram as electricity and magnetism combine to form the electromagnetic interaction, and electromagnetic interaction along with weak interaction can form electroweak interaction. Electroweak interaction with strong interaction can form grand unified interaction. Moving to the left side, terrestrial gravity along with astronomical gravity form gravitational interaction, and this gravitational interaction and grand unified interaction for combine to form universal interaction which holds the universe together in firm. The relative strength of various interactions span about 10 raised to the power of 39, and the distance through which they are effective are also very different. While the strong forces between nearby nucleons completely overwhelms the gravitational force between them when they are millimeter apart, the reverse is true. The structures of nuclei are determined by the properties of strong interaction, while the structures of atoms are determined by those of the electromagnetic interaction. Matter in bulk is found to be electrically neutral, and the strong and weak interactions are severely limited in range. Hence, the gravitational interaction, utterly insignificant on a small scale, becomes the dominant on a large scale. The role on the weak forces in the structure of matter is apparently that of a minor perturbation that seems to it that the nuclei with inappropriate neutron or proton ratios would undergo corrective beta decays. The universe would be very difficult if the strength of the various interactions had other values. For instance, if the strong interaction were more than a trifle stronger, the universe would be filled with diprotons, and the fusion reaction that give energy to the stars and create the chemical elements would not take place. If the strong interaction were weaker, protons would not combine with neutrons and also eliminate the exothermic fusion path to helium and heavier elements. The gravitational interaction is in a similar state of balance. If we're more powerful, stellar interiors would be hotter, the fusion reactions would occur more often, and the stars would eventually burn out sooner. Perhaps too soon for life to have developed on other planets. Significantly, weaker gravity, on the other hand, would not have clumped matter into stars to begin with. One of the tasks of a theory of everything is to establish why the fundamental interaction and the particles they affect have their properties they do. Now let's have a brief introduction on leptons and hadrons. Elementary particles basically fall into two classes, that is leptons and hadrons. This classification is based on depending whether they respond to strong reaction or not. The particles that respond to strong reactions are called hadrons, and the opposite are called leptons. The simplest particles that are leptons, which is evolved from a Greek language which means light or swift, which seem to be truly elementary with no hint of internal structures or even of extension in space. Leptons are affected only by electromagnetic, only if they are charged, and weak and gravitational interactions. Of the particles to which we have already been introduced, The electron and the neutrinos are found to be leptons, and also there are four other types which we'll look later. Now coming to hadrons, in Greek they mean heavy or strong. They are subject to the strong interaction as well as to the others. They also differ from leptons in that they occupy space rather than being infinitesimal in size. Hadrons seem to be a little over 1 Fermi meter, which is about 10 raised to minus 15 meter across. Hadrons are found to be are composed to be in two or three quarks, which like leptons are structureless and close to being point particles as present measurements can establish. Hadrons consist of three quarks, just proton, neutron, and are called baryons. Mesons such as pion consist of two quarks. Like nothing else in nature, quarks have charges of plus or minus 1 by 3 e or plus or minus 2 by 3 e, and their combination in hadrons is always such that the hadron charges are either 0 or plus or minus e. Quarks have never been observed outside of hadrons, but as we see, there is a convincing evidence that they do not exist. The strong force that acts between hadrons is the external manifestation of the more basic interaction among the quarks they contain, and it's mediated by the exchange of mesons, which will be described in the further sections. That's the end of the section. Thank you.